right, today what we're going to do is we are going to talk about checking the endpoints of our intervals of convergence for power series. Now, up to this point, we haven't really worried much about the endpoints of the interval of convergence. However, there are times in special cases when the endpoints will also converge and have a series that actually has a closed interval on one end, open on the other, or both closed end. And the process is very simple. It adds just two more steps. You have to check each endpoint. So it all starts with trying to find the interval of convergence in the first place. So let's do that for this series here. Using the ratio test, we're going to say that the sum from n equals 1 to infinity of, the ratio test is the limit. I get carried away sometimes. All right, the limit as n goes to infinity of the absolute value of the n plus 1th term, which would be x minus 2 to the n plus 1 over n plus 1. And I'm going to take the liberty of flipping the other term right now and save us some space. So this will be x minus 2 to the n. And if I simplify that, limit as n goes to infinity, I like to congregate the n. So this will be n over n plus 1. And then what's left here, the n1s cancel, and we're left with x minus 2. And this limit will equal the absolute value of x minus 2 because as n goes to infinity, this approaches 1. So this series will converge if the absolute value of x minus 2 is less than 1. And that means it'll lie between, x minus 2 will lie between 1 and negative 1. And then we're going to solve this inequality, and we're going to get 3. And when we add 2 to this side, we'll get 1. So our interval of convergence is going to be, if we use our little TIE fighter, 1 and 3. And the center then is 2, which makes sense that the center would be 2 because it's x minus 2 up here. Now, the only difference between what we did last time in finding intervals of convergence and this time is that we're going to check the endpoints for convergence. So what I'm going to do is I'm going to take a moment here in checking the endpoints. Now, what do I mean by that? That means I'm going to actually let x equal 1. So what happens when x equals 1 to my series here? All right, so we're going to plug this in, and I get the sum as n goes to infinity of, well, when I plug all this negative 1 to the n, that's not affected, but this is. So 1 minus 2 is negative 1, so this turns into negative 1 to the n all over n. Okay, and I can add like terms or multiply with the same base here, and I get the sum from n equals 1 to infinity of negative 1. Now, n plus n is 2n all over n. And I can rewrite it one more time because 2n is an even number, right? Anytime you have n as 1, that's 2. N is 2, that's, you're just always going to get an even number. So with 2n being an even number, negative 1 raised to an always even number will be positive. So this is 1 over n. And believe it or not, last time we discussed this is the p series. And actually here p is 1. Therefore, diverges at x equals 1. So this is going to remain open here, all right, for that endpoint. The second endpoint is at x equals 3. So let's see what happens when we plug in x equals 3 to our series up here. So when I plug 3 in here, I get 3 minus 2, which is 1 to the n. So I'll write that. So we get the sum from n equals 1 to infinity of negative 1 to the n times 1 to the n all over n. And if you simplify this, you're going to get the sum from n equal 1 to infinity. Well, 1 to the n is just 1. So uh, this will go away, this term will go away. And so then I'm still alternating. Now, since this is an alternating series, I'm going to use the alternating series test, a test designed just for alternating series. And I'm going to suggest that the limit as n goes to infinity of the non-alternating piece, which is 1 over n, does go to 0. So that's the first condition. The second condition is that a sub n is greater than or equal to a sub n plus 1, which is essentially your terms are getting smaller or are the same. So let's see what happens when I plug in n. I get 1 over n. Is that greater than or equal to 1 over n plus 1? And this is true because the larger your denominator is, the smaller your fraction. So that works. So guess what? This series converges at x equals 3. So my IOC, if I have my final answer here, my IOC, my interval of convergence, is going to be from 1 to 3 with a bracket. And so this actually turns into a bracket. All right. And we say by alternating series test here, we should say why it converges. All right, so that's not too bad. You do the ratio test as we know how to do, and then you just do two more series checks for convergence to see if they will converge when x equals 1 or x equals 3. Let's try another one. Let's try this one. Obviously, we're going to find the interval of convergence first. By using what? The ratio test. All right, when I do that, I'm going to have to do the limit as n goes to infinity of, this is going to be absolute value of 2x minus 1 to the n plus 1 over n plus 1 quantity squared times, again, I'm going to take the liberty of flipping this already. This is n squared over 2x minus 1 to the n. And the 2x minus 1 to the n's cancel, and let's see what we're left with here. The limit as n goes to infinity of, now I like to keep the n's together, so this is n squared over n plus 1 quantity squared, and I'm left with 2x minus 1, because I'm left with the one of them up there. And this equals the absolute value, because this goes to 1, again, nicely, of 2x minus 1. All right, so this series will converge when the absolute value of 2x minus 1 is less than 1. And so that means it'll lie between negative 1 and 1, 2x minus 1. And then I add 1 to all sides, and I get 0. And this will be 2 on this side. And then divide everything by 2, and I get 0 and 1. So my interval of convergence initially, with a center of 1/2, goes from 0 to 1. Initially. But what do we have to do? Well, we have to check the endpoints. All right, so checking the endpoints. Well, what are the endpoints? Well, it's x equals 0, which we like to plug in. So I like to say x equals 0 here, And that means I'm going to have the sum from n equals 1 to infinity of, when I plug 0 in my series, I'm going to be left with negative 1 to the n over n squared. And this is an alternating series. So using the alternating series test, I have to check those two conditions. And those conditions are, does the limit as n goes to infinity of the non-alternating piece go to 0? Well, the answer is yes, because 1 over n squared definitely goes to 0 as the n gets very large. And then, are the terms getting smaller? Is a sub n always greater than or equal to a sub n plus 1? So let's plug it in and see. That would be 1 over n squared. Is that greater than or equal to 1 over n plus 1 quantity squared? And I would say that that's absolutely the case because this denominator is bigger than this one. So this fraction will be smaller. All right, so series then converges at x equals 0 by the alternating series test. All right, so that means this is a bracket here. The TIE fighter is getting squared off here. All right, what about the next endpoint? We'll try x equals 1. Let's see what happens when we plug 1 into our series. When we plug in 1, we're going to get 2 minus 1, which is 1. And so that'll be 1 to the n. So this will be the sum from n equals 1 to infinity of 1 to the n over n squared, which is the same thing as saying n equals 1 to infinity of 1 over n squared. And I really like to see this because I know that that's what kind of series? Oh, I heard it. P series. Right. And P is equal to 2, which is greater than 1. Therefore, the series converges. Can I spell converges? The answer is no. Converges at x equals 1 by the P series. I guess we'd call it P series test. All right, so which means I have a bracket on this end. So the IOC for this problem is 0 to 1, and both endpoints are included. All right, so let's do another one. Let's do one with factorial, because sometimes factorials can be a little scary, but you know they shouldn't intimidate you because the ratio test always helps us out with factorials, which is really nice. All right, so the very first step is we're going to be finding the interval of convergence using the ratio test. Well, what is the ratio test? It's the limit as n goes to infinity of the absolute value of, well, this is x to the 2, and where I see an n, I'm going to put n plus 1 all over 2 times n plus 1 factorial times, and I'm going to flip it, and we're going to get 2n factorial on top over x to the 2n. Now I'm going to simplify this a little bit because we want to be smart about how we simplify this. So this is going to be 2n plus 2 plus 1. So this will be x to the 2n plus 3 on top here over, and this is going to be 2n plus 2 factorial times 2n factorial over x to the 2n. Absolute value, okay? And then we know that the 2n's are going to cancel. And so this term goes away. And then inside of this 2n plus 2, we have a 2n plus 2. We have a 2n plus 1 times 2n factorial. So we can cancel the 2n factorials. And we're left with the limit as n goes to infinity of Well, it looks like it's going to be, let's see here. Oh, this is not plus 1, is it? Sorry. This is 2x to the 2n plus 1, which is the 2n plus 2. You know, I had that nagging feeling I had written something down wrong. All right, which is going to equal, momentary lapse of reason, right? X squared over 2n plus 2, 2n plus 1. It's a lot harder to do these videos when I'm not in class with you guys, because if I make a silly mistake like that, you guys catch me right away and I can go right back and fix it. And then when I'm working, sometimes I'll see, oh gosh, you know, something doesn't feel right about this. And then I have to go back and find it myself. So believe it or not, I appreciate you guys. All right. The limit as n goes to infinity of this situation, in here, the x squared over the 2n plus 2 times 2n plus 1, x is just a constant in this case because we're letting n go to infinity. So this is going to go to 0. So if this limit goes to 0 and it's less than 1, by the ratio test, it doesn't matter what x is. So we can say by the ratio test, this series converges for all real numbers. So its IOC is negative infinity to infinity. And good news for us is that there's no need to check the endpoints here. I hear cheers from the background, I know. Yay, no need to check the endpoints. Okay, now, this is one of the conditions. Remember, there are three options. There are three options when we're dealing with convergence. You can either be convergent for all real numbers like we just proved here. You can be convergent over an interval, which we've just done 2 of. And you can just be convergent at a single point where this goes to infinity. And the only way this expression will be 0 is if x is 0. So we've done an example of each of those, which is pretty cool. All right, moving right along. All right, this one here, we're going to do the same thing. We're going to find the interval of convergence using the ratio test. The limit as n goes to infinity of absolute value of x, or 1, I'm just going to put this in the denominator, 2 to the n plus 1. And then this is going to be x minus 1 to the 2n plus 1. Now 2n plus 1, n plus 1 has to be in here plus 1. I must have anticipated on the last problem that I was going to have to do this for the next one. Times, I'm going to flip it, 2n over x minus 1 quantity to the 2n plus 1. All right, let's simplify that a bit. The limit as n goes to infinity of, well, the n, 2 to the n's are going to cancel, and I'm left with 1, 2 on the bottom. And I know that this denominator, I'll do the numerators real quick because it's really important that we get this straightened out. So I've got to distribute this. So this would be 2n plus 2 plus 1. So this is going to be x minus 1 to the 2n plus 3. There it is. That's the one I knew I was going to have to do. Times 1 over x minus 1 to the 2n plus 1. With the limit as n goes to infinity of, the 2n's cancel, and I'm left with absolute value of x minus 1 to the second over 2, because all the n's cancel out. So what is this limit if the n, I'm taking n to infinity? Well, the limit is just going to be what the x thing is here, which is x, the x expression. So x minus 1 quantity squared over 2, absolute value of that. And this will converge if the absolute value of x minus 1 quantity squared over 2 is less than 1. All right. Now, this is a little tricky algebraic thing to solve, but because you need to solve it in a certain order in order to not have a non-real answer. And so this is how I do this. First thing I do is I move the 2 over. So we're going to have the absolute value of x minus 1 quantity squared is less than 2. And since we're squaring this, the absolute value bars, since this term is always positive, right? When you square something, it's always positive unless this is 0, which is at x equal 1, which is the center, which I'm not necessarily worried about. But anyway, I can drop the absolute value bars because they are redundant. Because this term is always positive, and except for the one time it's 0, so we don't need them, the absolute value bars. So I can drop those and say x minus 1 quantity squared is less than 2. Now, I know we've talked about in the past, when you take the square root of an absolute value, or of a square like this, you're going to get the absolute value of x minus 1 is less than root 2. And now I can do this with ease because I know it's going to be negative root 2. It's going to lie between, oops, helps if I write the right inequality here, x minus 1. So it's x minus 1 is going to lie between negative 2 and negative root 2 and positive root 2. And then if I add 1 to each, we're going to get x lies between 1 plus root 2 and x lies between 1 minus root 2. So my IOC is going to be my little TIE fighter centered at 1. This will be 1 plus root 2, and this will be 1 minus root 2. Now, what do we have to do when we're doing these? We need to check the endpoints, okay? So checking the endpoints. Let's see if I can squeeze it on this page. I'll try not to write too small. Just want to keep it all together. Okay, so what are the endpoints of our interval of convergence? Well, the first one is 1 minus root 2. So I'm going to try it at x equals 1 minus root 2. Okay, when I do that, this sum becomes n equals 0 to infinity of, when I plug 1, we'll plug it in. 1 minus root 2 minus 1 all over 2 to the n. This is raised to the 2n plus 1. Okay, the 1's cancel. Then I'm left with the sum from n equals 0 to infinity of negative root 2 to the 2n plus 1 all over 2 to the n. All right. The sum from n equals 0 to infinity of negative 1 to the 2n plus 1 times 2 to the 1/2 times 2n plus 1 all over 2 to the n. All right, now I'm going to distribute this 1/2 here. And we're going to get negative 1 to the 2n plus 1, 2 to the n plus 1/2, all over 2 to the n. Now, the 2 to the n's are going to cancel here, and then I'm going to be left with just on top here negative 1 to the 2n plus 1 times 2 to the 1/2, which is the square root of 2. Okay, now, what kind of number is 2n plus 1? Now, when I say what kind of number, I'm asking whether it's even or odd always. Well, this number is always odd because you're taking an even number and adding 1 every time. Because remember, I said 2n is always even. And when you add 1 every time to an even number, you're going to get an odd number. So this is negative 1 raised to an odd number forever. So that means my series could be rewritten as this: n equals 0 to infinity of negative root 2, taking away the n completely, and that is, I'm going to take the limit as n goes to infinity using the nth term test for divergence of negative root 2, and I'm going to get negative root 2, which is not equal to 0. So this diverges by the nth root test. Nth term test of divergence. Now that was some tricky exponential, work there. So this IOC is going to remain open on the left-hand side. Okay. Now I'm running out of space, so I'm going to do the other endpoint over here. So it'll be space as a premium here. So x equals 1 plus root 2. So hopefully this one will be a little bit easier. What happens when we plug in this into the sum here, 1 plus x root 2? And it goes from 0 to infinity, and then we're going to have 2n on the bottom, and then we're going to have 1 plus the square root of 2 minus 1, which is going to give me the square root of 2 to the 2n plus 1. All right, and that's going to equal the sum from n equals 0 to infinity of, that's going to be 2 to the n plus 1/2. Remember, because we simplified that on this side over here. And there's no alternating piece here, or always negative piece here. And the 2 to the n's are going to cancel, and then I'm going to be left with just the sum as n goes from 0 to infinity of the square root of 2, which also diverges by the nth term test, because the limit as n goes to infinity of root 2 is equal to root 2, and that's not equal to 0, so this diverges by nth term test. And so my IOC, by its very definition for this problem, remains 1 minus root 2 to 1 plus root 2, and it's open on both ends. Yeah, some messy exponential work on that one, but it's kind of fun. All right, next one. I figured I'd go through some multiple choice questions just to get you to know what I'm thinking when I solve some of these. And the first one is this one. Given the series negative 1 to the n e to the n over n squared when n goes from 1 to infinity, they're saying this diverges because, well, the terms do not tend to 0 as n goes to infinity. So the very first thing I'm going to do is see what's true and what isn't. So number 1, I'm going to check out the limit as n goes to infinity. This is, I'm going to use, actually this is alternating, so I'm using the AST, alternating series test, and I meant to make a little Roman numeral here, because that's what we're checking with the alternating series test, right? That the terms do not tend to 0, or they do tend to 0. So the limit as n goes to infinity of the non-alternating part is e to the n over n squared. Now, technically, but on multiple choice, you don't have to show this. This is infinity over infinity. So we can use L'Hopital, which would be the limit as n goes to infinity of e to the n times the derivative of the exponent, which is just 1, over 2n which is still infinity over infinity. I can take the derivative one more time, and that would be e to the n over 2, which will definitely be infinity. And therefore, these terms do not tend to 0. So this is true. So I know it's got to have a 1 in it. So I can cancel out this one and this one because I know I have to have a 1 at least. And then the terms are not all positive. Well, that, I don't know about that one yet. Let me try this limit here to see what happens down here. So we'll take the limit as n goes to infinity, because this is the ratio test. And if it's greater than 1, regardless if it's alternating, we already said it fails the alternating series test. So I suspect it's going to fail this test too, but let's see what happens. I'm going to take the non-alternating piece, and I'm going to say e to the n plus 1 over n plus 1 quantity squared times n squared over e to the n. And I can get rid of the e to the n's, and I'm going to congregate my n's. I get n squared over n plus 1 quantity squared times e. Well, guess what, folks? This n rational goes to 1 as you let n get really big because it's degree 2 over degree 2. And so my limit then is e, which is greater than 1. So by the ratio test, this diverges. And this diverges. So the terms are not positive doesn't really affect it because this is alternating, and we use the alternating series test. So it didn't diverge because all of the terms are not positive. So the answer is going to be 1 and 3. All right, moving right along. Interval of convergence for the series. Now notice in this one, the interval of convergence has some equalities and inequalities here, which means they're trying to get us to check the endpoints. Okay, so IOC using the ratio test. We get the limit as n goes to infinity of the absolute value of 3x plus 2. Now this is n plus 1. When I plug in n plus 1, I'm going to get n plus 1 plus 1, which is n plus 2, over n plus 1 to the 5 halves, times, I'm going to flip this apart, n to the 5 halves, over 3x plus 2 to the n plus 1. The 3x to the n's cancel, and then I'm left with 2 minus 1 here, which is just 1. So this will be the limit then as n goes to infinity of the absolute value of, I'm going to congregate the n's, and you'll notice that again we have that same situation where everything's raised to the same exponent, meaning that this limit's going to be 1 times 3x plus 2 to the first, which means my condition for convergence will be 3x plus 2 has to be less than 1. So we'll converge when absolute value of 3x plus 2 is less than 1. Now, of course, when you're doing multiple choice, you don't have to write all these words. I'm just doing this so that you can see my thought process. I'm sure you could do this a lot faster without having to justify all your answers and stuff, but I just wanted to show you how it worked. All right, so this will converge when this expression, 3x plus 2, lies between negative 1 and 1. Solving, we're going to subtract 2, so this will be negative 1 over here, and then this will be negative 3. Dividing by 3, I get negative 1/3 is less than, that's 1 on this side. Now, I'm going to notice right away that can I eliminate 2 of the choices? Well, because I need negative 1 on the left and 1/3 on the right. Well, I can eliminate that one because that's a no-go. And I can eliminate this one because that's a no-go. And I have to worry about A, B, and C now. All right, so we're going to check the endpoints. And what is our clue that we have to check the endpoints? Well, we've got equalities here, so we gotta check the endpoints. All right, the endpoints are at x equals -1. Let's plug -1 in our series here. When I plug in -1, I get -3 plus 2. -3 plus 2. That means we're going from 1 to infinity here. That's a -1 to the n plus 1. All over n to the 5 halves. Now, does this alternate? The answer is yes. So, I'm going to use the alternating series test. The first test of it is the limit as n goes to infinity of 1 over n to the 5 halves. Does that go to 0? Well, yes, it does. The second part of that test are the terms getting smaller? So is a sub n greater than or equal to a sub n plus 1? So a sub n is 1 over n to the 5 halves. Is that greater than or equal to 1 over n plus 1 to the 5 halves? Well, which denominator is bigger? Well, this denominator is bigger, so this fraction here is smaller than this one. Check. So this one converges at x equals -1. So I have to have an equals on the -1 part of this. So now I know I can eliminate this one. And so clearly I have to check the x equals -1/3. What happens when I plug in -1/3 in for x up here? I get -1 plus 2 is 1. So I get the sum from n equals 0 to infinity of, that's going to be +1 to the n plus 1 over n to the 5 halves. Now 1 to anything is just 1. So this is n equals 0 to infinity with 1 over n to the 5 halves. And guess what, folks? This is a p series with p greater than 1. So this converges by the p series. P equals 5 halves, which is greater than 1. So the endpoints are going to have to be included. So if the answer is C. Okay, moving right along. I also figured while going through this stuff, I would combine Taylor series knowledge in some of the multiple choice here. And this is a common type question that you might see. It's given that f of x equals this series here on the interval of convergence of the Taylor series, which means if it's on the interval of convergence, it's going to be something we can use to approximate the function. The fourth derivative of a equals what? Well, if I let n equal 4, my fourth term is going to be the fourth derivative of a times x minus a to the 4th over 4 factorial. Okay, and I'm going to set that equal to, what would this be when I let n equal 4? Well, that's just going to be 4 times x minus a to the 4th over 2 to the 4th. And what's common to both of these things? Well, the x minus a to the 4th, so I can cancel those out. And so then I'm left with the fourth derivative evaluated at a is going to equal 4 factorial times 4 over 16. And if you simplify this a little bit, this is 4 times 3 times 2 times 1 times 4 all over 16. And that will simplify to 6. So our answer is 6. So you don't have to expand the entire series just to see what the fourth derivative evaluated at that point is. Okay, that's kind of a neat trick, and I've seen this a lot on the exam. All right. I see this kind of question as well a lot of times, and you're like, oh gosh, this is a top secret way to get us to have to do three series convergence tests all at once in one problem. And it's tricky and not very nice. All right, but anyway, let's go through it and see what happens here. This one here is n squared minus n plus 5 over n to the 7/2 plus 1. And when I look at that, I go, you know, I really wish that I had only n squared over n to the 7/2. So when n gets very large, number one, I think, will behave like the sum from n equals 1 to infinity. Whoops, that infinity is a little bit high there. Infinity of n squared over n to the 7/2. Okay? And you can do direct comparison and the limit comparison test or the limit comparison test, and you'll see that they do indeed behave similarly. But I'm going to apply to your intuition, and when n gets very large, these don't matter very much. And so this is going, and this, if you simplify, it goes from n equals 1 to infinity of 1 over n to the 3/2 if you go 2 minus 7/2 on the bottom there, which is a p series where p equals 3/2, which is greater than 1. So 1 is definitely one that does converge. So we know that. So what can we eliminate down here? Well, we can eliminate 2 and 3, and we can eliminate none of them do. And now we have to check this one. Now this one, I hope you notice right away, is an alternating harmonic. And I hope that you will memorize that the alternating harmonic which means p equals 1, converges by the alternating series test. Because it's the limit as n goes to infinity of 3 over n equal to 0? The answer is yes. The answer is yes. And the limit as n goes to, I'm sorry, not the limit, I'm sorry, are the terms getting smaller? A sub n greater than or equal to a sub n plus 1. That means 3 over n, helps if I put a 3. 3 over n greater than or equal to 3 over n plus 1. Yes, because this denominator is bigger, making this fraction smaller. So yes, this is true. So the alternating harmonic will always converge when the non-alternating harmonic does not, because of the p series being equal to 1. All right, so we know that 1 and 2 will work. But sadly, that eliminates b. And now we said that, yeah, this is nice, really nice. With all that work that we've done so far, they are going to make us check this last one. Well, and the last one, to be really honest, is the most interesting one, I think. It's the sum from n equals 1 to infinity of cosine of 2n pi over n squared. So when I see a trig function, what I like to do is expand the first couple of terms so I can actually see what the series is doing. So we're going to let n equal 1. When you let n equal 1, cosine of 2 pi is 1. 1 over 1 squared is 1. Now let's let n equal 2. N equals 2. This is cosine of 4 pi. And it'll be cosine of 6 pi. It'll be cosine of 8 pi. So what's happening here is, remember, on the unit circle, all the even pi's are on the right-hand side, and all the odd pi's are on the left. So this is always going to be cosine of an even-numbered pi, which this will always be 1. So crazily enough, this series is going to be... To whom should I... Siri just thought I was talking to her. That's hilarious. Sorry. So I can rewrite this series as n equals 1 to infinity. I have to be careful what I'm saying around my phone. 1 over n squared, which is a p series with p equal to 2, which is greater than 1. So this one will also converge. So they all do. What a sneaky way for us to check all 3 of them. All right. This one is one of my favorites because as much as you don't want to memorize that list of Taylor series or Taylor-Maclaurin series for those that list e to the x, cosine x, and all of those kind of things, this is the kind of problem where you really need to know what they are, because this is 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial plus dot, dot, dot. This is an alternating series that looks suspiciously like negative 1 to the n x to the 2n over 2n factorial. And whose series is this? Well, it happens to be cosine x's series. So what are they doing here? They're saying this is cosine x evaluated at pi. And well, what's cosine of pi? That's just negative 1. See, so recognizing that this is an alternating series and all of the powers are even, and this is the cosine evaluated at x equals pi, is pretty cool, I think. And so that is the end of checking my endpoints on intervals of convergence and some extra practice on solving multiple choice questions. Hope you have a great day.